So, good morning, all of you. So, we would start from where we left in lecture 17. So, today our agenda would be to finish up with Gram-Schmidt orthogonalization procedure, a very important procedure because in order to study modulation schemes, which we will be doing towards the end of the course, we need this. Okay, it means we need an orthonormal, you can say, or orthogonal set of time-limited signals. Okay, because that is a pulse. So, in order to means, let us say we are doing everything in respect to 0 to t, where t is the bit interval, and we are trying to create any sort of pulse in 0 to t such that it satisfies some properties in the frequency domain. Okay, so in order to design systems around that thing, we need this orthogonal set which allows us to study the systems more properly. So how do you create an orthogonal set of signals which are let us say defined in 0 to capital T? That is what this procedure tells us. So in order to go through this procedure, we wanted some base to be built with respect to projection of one vector onto another vector. So we did some initial study in last lecture, so we'll just revise it quickly and then we would start with the remaining part. So we were studying the component of a vector along another vector. Now when we say that, let us say this x bar is, so we are using the notation in which we put a bar on the variable to denote that it is a vector. Okay, we have not yet specified that whether this is a 2-dimensional vector, 3-dimensional vector, or an n-dimensional vector. For say, assume that this is a vector which we can visualize like this. Okay, in some space, it is by this line segment, you can say g and x. Now anything along x would be of the form c of x bar. There would be only a scaling of c, which is a scalar of the same vector, if we say there is a vector along this vector x bar. Why? Because this vector will share the same direction as x, only the magnitude would be different. So if we say that a vector g has a component along this vector x, it has to be of the form c x bar. Now we have not yet specified what do you mean by the component. So first of all, let us study what we already know. So we know that component of g along x is c x bar. That is what I already told you. Geometrically, the component of g along x bar is a projection of g on x and is obtained by drawing a perpendicular from the tip of g on the vector x. Okay. So this says that c x bar plus e bar will be g bar, and e bar is perpendicular onto x, and this is called as a projection of g on x. Now, what do we recall? See, if the angle is theta, then we recall from our you can say school days that the component along x would be g cos theta, and along the orthogonal direction would be g sin theta. So that is done believing that this will be a perpendicular onto this. This we know. Okay. In geometry, we have studied that if this angle is theta and this is you can say this is a right angle triangle, it means this is a 90-degree angle. Okay, so if this is a 90-degree angle, then I can write the component this and this in terms of this theta and this vector. Okay, so this is g cos theta and g sin theta, that you already know. But then the question is, so what is the mathematical significance of a component of a vector along one vector? ये तो हमें पता था, this is what we knew. But we started with the point that we first study component of a vector along another vector. So the question is, what is the mathematical significance of a component of a vector along another vector? So we saw that if at all our desire is to write g in terms of a component along x plus another component, there are several possibilities. Okay, I wanted to show you this figure from the textbook, let us say B.P. Latti's book, but somehow this was missing. This figure is not there in the e-copy which we have, but in the hard copy these figures are there. So for the sake of completion, I have drawn these. So B.P. Latti has shown several of these possibilities in which you can have some e vector which starts from some arbitrary point on x and it goes to g. So it means that g can be written as c1 x bar plus e1 bar. Okay. So these are two of the infinite other possibilities. So from the perspective of vector addition to another vector, what is the best decomposition? Okay. So if at all our aim was to find the component of a vector g along x, so that we can write g as sum of a component along x plus another vector. So there are several such possibilities. Two possibilities from the infinite set I have drawn for you. Okay. So from the perspective of vector addition, what is the best decomposition? Okay. So at this point we stop. So let us go ahead and see that what we can do. So aim was, our aim was, to write GSC x bar plus some e bar, okay, in the last lecture. So the question was, what is the best decomposition of this form? Okay. So first of all, we need to say that, so the answer is, first of all, we need to argue. The answer starts from argument that the concept of optimality depends on what we wish to accomplish. Okay. So that is quite obvious from the question which I have written, that really what do we want to achieve? Best decomposition means you need to define the criteria of optimality. That you will say that this decomposition has some metric of optimality, and you do all possible decompositions and compare the metric of optimality. Whichever gives you the minimum, if that is the criteria, that is the best decomposition. Okay? Accomplished by decomposing G into two components. Okay, so the answer to this is that we can think of E being the error in approximating G bar by Cx bar. If we think that way, we can think of E bar being the error in approximating G bar by Cx bar. Hence, if we do this, if we think like this, hence we can now define mathematically the component or projection of a vector G bar along vector x bar to be Cx bar, where C is chosen to minimize the the magnitude of error vector E bar, which is equal to G bar minus C x bar. I think it is all self-explanatory once I have written everything, that if we assume E bar to be the error in approximating G by C x bar, so our obvious criteria of optimality would be to minimize the norm of E bar. It means जो magnitude आ रहा है error का वो सबसे छोटा होगा, वही हम एक optimality के criteria set कर सकते हैं, and that is leads to the concept of, you can say, orthogonal projection. Okay. So you can see, so we are not proving it, because I think you must have done all these things in your earlier courses. For example, groups and linear algebra. In linear algebra, this topic is quite well studied. So I'm just, you can say, refreshing a few points of that course. So you can see that, the perpendicular, that E being perpendicular, or orthogonal, you can say. Instead of perpendicular, I should write orthogonal. Or for the time being, let us assume perpendicular. Has the smallest magnitude. See, I am not proving this because this, I think you can easily do it. If you are not able to do it, you can refer to the textbooks of linear algebra to get the proof of this. The smallest magnitude or norm, and it is the unique one. So I am writing it in the inverted comma. It is the unique one. Okay, so this should be minimum. That it is the unique. Indeed, it will be the unique thing. That only one, you can say E exists, which is orthogonal to X, and that E will give you the minimum norm error, or that will give you the minimum error in approximating G via CX. Okay. So this is what we wanted to have around the concept of projection, that we are approximating one, let us say, vector in terms of another vector in such a way that the error in approximation should be minimum. And if we set that as the criteria of our, you can say, this sort of decomposition where we want to write G as sum of two vectors with the C of x bar plus E bar, then that way E has to be orthogonal or perpendicular to x bar, the vector on which you are projecting the other vector. Okay. So this is, you can say, a sort of hand waving type of argument, because we are not proving a few of our statements, assuming that they are either easy to show or we have already gone through them. Okay. Now let us see a few concepts around it. So we know that when E is orthogonal to x bar, you can write that C norm of x bar must be equal to norm of G bar cos theta. Okay. Now why is this? Let us see it. Suppose this is your G. This you already know, and this is suppose your x. And I say that I am drawing, okay, this is my E bar. So you know that if this angle is theta, so this component we already studied that this is G bar cos theta. Okay, and this we are denoting the same vector. Let us, I think, should not draw this. Let us keep the direction intact, concept of direction intact. Also not we should use the same vector, that is, this is what is like this. Okay. And this is, let us say, you know that this is G bar cos theta, and we denote it by, we have denoted it by Cx. So you know that now. So we are now seeing the norm of this. We have not yet said what is C. C can be positive or negative. Why? Because it will be decided by this angle theta. There is one case is like this, another case is like this. If suppose you have this sort of a configuration where this is your G bar, this is your X bar, then you will try to have like this. This is your bar. Now this has an opposite direction to that of X. So anyways, if at all cos theta is negative, C would be negative, and they would basically cancel out each other. So you can say that the way we have written above. Otherwise, you would say that why aren't we placing an absolute value operator around C? It means it should be a positive quantity if we are simply saying that this is the norm. Okay, but it would subsequently cancel out. If C is negative, cos theta would also be negative. Okay, by the logic of projection. So let us multiply by x, norm of x, both sides. Basically, we are doing a few derivations, you can say, in a different manner. This is the approach which is used by B. Pilati, but I have found out that the approach is good if at all you have some base in the area. Approach is good. Why? Because it gives us the thing in concise manner. Okay. Otherwise, you would be lost studying these points only. Otherwise, and our purpose is to undergo digital communication course. Okay. So then what it leads to is, if you multiply both sides, then we get that C norm of this square must be equal to norm of G bar into norm of X bar cos theta, which is equal to the inner product of G with X. I think this we must have done in our earlier, I think, lecture. We have done it or not? Let us see. Okay, I think if you have not covered it, so I would write that this is the standard inner product in the Euclidean. Inner product we have introduced somewhat, but we have not specifically said that this is norm of this into cos theta. Okay. Anyways, we can define it now. So this is the inner product. Inner product, and it is defined in, and it is, so that it can be defined in, it can be defined in this manner. Okay? So we know that now C is equal to the inner product of the two vectors divided by, okay, what it is, because this is nothing but square. Okay. So what can we see? So this is the constant, or you can say the scalar, which this can be easily obtained by finding the inner product of G and dividing it by the self inner product, or you can say the norm square. Okay, because what is norm is under root of this. If at all, I think we must have done it in the last class or last lecture, that this is this under root of this. So if you square it, we get that. So we can see that when G and X bar are orthogonal or perpendicular for C, then G has a zero component along X bar. Okay, that is quite obvious. Why? Because the logic which we have used is that if at all this is the scenario, this is X bar and this is G bar. Okay, then obviously from the way of, or from the design or from the concept of projection we have employed, you cannot find, if at all there is the error vector which is there, that is G itself. Okay, it means you cannot have any component of G along this. C is 0 because G itself becomes the error vector. When G itself is the error vector, it means you cannot represent G in terms of any vector along X. मतलब G अपने में ही पूरी error है, means इसका कोई component possible ही नहीं है इसका. That is what this design criteria gives us. Okay. Consequently, C is 0. Consequently, C is 0. Okay. Hence, G and X are said to be orthogonal. X are said to be orthogonal if the inner product scalar or dot, you can see, because in the Euclidean space this is also quite popular, that is called the scalar product or dot product of the two vectors is 0. That is, if this is 0. So this is one of the, you can say, a short version of saying that if you want to see if the two vectors are orthogonal to each other, you simply take the inner product and if that has to be 0. But that implies that this vector has no component along x. So this shows that this is orthogonal. Okay, so this is, you can say, some sort of a circular way of saying things, because we know that with the inner product or the dot product, so I should write that this is the inner, you can say this is the dot product, standard dot product, which we use in the n-dimensional Euclidean space. Why I didn't say dot product before is that we have not yet specified what G and X are. We have not yet specified the dimension as well. But for the times being, we can assume that we are working in, you can say, some n-dimensional space, and it has some sort of a, you can say, parallel with the Euclidean space. So for in the case of Euclidean space, all these things are well defined. One more thing, that such things have parallels for all possible spaces. It means you can say a space of matrices and everything. Once you find the basis, then after the basis, most of the things which you have in Euclidean space will easily follow for such spaces as well. So this is what all we required in terms of projection and this. Now we will start with the Gram-Schmidt procedure. So I would write the Gram-Schmidt continue. Okay. So given m energy signals. Now by energy signals we mean that their energy is finite. You should not have any signal whose energy is infinite in the set. It's denoted as S1t, S2t, Snt. How do you create a complete orthonormal set of basis functions? Okay, that is the question. Now, what is the meaning of word complete? Complete means that this orthonormal set, through this orthonormal set, you must be able to write each of the m functions. Okay, that is the meaning of complete here. Let us say this orthonormal, let us say this m is 4, and this orthonormal set has two functions. So in terms of those two functions, you must be able to write all these four functions. Okay, so that is the purpose of saying complete. So with this procedure, we want to find a complete orthonormal set of basis functions. Now, orthonormal means that those functions or those elements of this set must be orthogonal to each other, and orthonormal means that their norm must be 1, and basis means that each of the vector m vectors must be able to be expressed in terms of these functions. Okay, so this is the breakup of the sentence. So how do you do that? The first step is start with S1. What do you do is start with S1. Okay, chosen from the set arbitrarily. This is important to write. Chosen from the set arbitrarily. It means the first function which you consider, it can be any of the n functions. Let us say capital N is 4. So from 4 you can choose any function. Okay, you start with S1T chosen from the set arbitrarily. मतलब आप किसी भी function से start कर सकते हैं. The first basis function is defined by phi 1t is equal to S1t divided by root of E1. Okay. What is E1? That is the energy of S1t. Now what does this mean? Now phi 1t has a unit norm. Okay. If we try to find out the energy of phi 1t, let us write what is the energy of phi 1t. If I assume that they all lie from suppose 0 to t, so we will do 0 to t S1 square t divided by E1 dt. This is equal to 1 upon E1 into E1. So we have assumed that they are over, we are studying over 0 to. So you can find out that phi 1t has a unit energy. Now let us go to step 2. First of all, let us say then clearly. So then clearly S1t is equal to root of E1 phi 1. Okay, which is equal to, suppose this is S11 phi 1. Now second, define S21 as, now what you do is you find the inner product or you find the projection of S2t onto phi 1. Okay. T of t divide by 0 to t phi 1 square t dt. Okay. What is this? This is component of S2t along phi. This we have already studied. How do you find the component? This is basic, nothing but the inner product of S2t with phi 1t and divide by the, you can say, the norm square of the vector on which I am projecting. So I am projecting on phi 1. Okay. Now you know that this is nothing but, this is 1 by the design. We have already shown that this is the energy of this phi 1t is 1. So when S21 is defined like this, now what you do is you create another signal which is now orthogonal to phi 1t. How do you do that? You simply take this signal and subtract the component of it along the. So what we have done is, this is basically the error in approximating S2t by S21 phi 1t. We know by choosing S21 as in equation 1, then 1, G2t would be orthogonal to phi 1. So this we know. I think this we have already studied. I think we were doing this. So we have created at least second signal which is now orthogonal to phi 1t. Now what remains is we need to scale it so that the energy is 1. Okay. So we know by choosing S21 as the G2t would be orthogonal to phi 1t over the interval. So we are doing all of this thing over some interval. Okay. Why this interval is taken? Because generally we would be concerned with signals lying in from some 0 to t, because though we have to use it for our transmission. Okay, क्योंकि ट्रांसमिशन करना है और उसमें एक स्ट्रिक्ट डेफिनेशन है बिट इंटरवल की. देयर इज अ कॉन्सेप्ट ऑफ बिट इंटरवल, सो दैट इज वेरी इंपॉर्टेंट. That's why we are studying signals which are which have these properties over 0 to t. क्योंकि ये t का बहुत बड़ा सिग्निफिकेंस है हमारे कम्युनिकेशन सिस्टम में जो हम स्टडी कर रहे हैं डिजिटल कम्युनिकेशन सिस्टम्स में. दैट वी नो दैट बिकॉज we this t mostly would represent the bit interval or the symbol. Okay, so second basis function would be, so we would write that the second basis function is equal to phi to t is equal to g to t divided by, you have to scale it by the energy. So how do you obtain the energy? You just simply square it. Okay, so we are right now dealing with all real functions, otherwise यहाँ पे absolute value square dt है. ये सब complex हो सकते हैं. Phi to t would then become complex because g to t itself would be complex. Okay, so right now we are studying only real value functions. Now simplify it. So simplifying, we get phi to t is equal to s2 t minus s21 y1 t divided by under root of e2 minus s21 square. Okay, what is e2? E2 is energy of s2. Okay, so we just simply substitute the terms and solve. You will do this. Okay, this, I think this is homework, I would say. This is okay, you have to do it yourself, quite easy to show. So what have we really achieved? Let's see. So now we have integral 0 to t phi to square dt is equal to 1. Okay, and as they, okay, it means they form, so they form an orthonormal pair. Okay, so हम लोगों ने what we have done is that we have obtained two functions, and that too from the set itself. हम लोगों को जो set given था S1 से लेके Sm तक का, S1t, S2t, Smt, and from this set itself we have created two functions which are orthonormal to each other. Now let us move ahead because we are not finished, because we want a complete orthonormal set. That is important. So continuing in this fashion, we have that GIT is equal to SIT minus Sij phi j, okay, where Sij is nothing but is equal to 0 to t SIT into phi j, and j is equal to 1 to average. Okay. Now what are we doing is, suppose we need to construct, let us see where I should write, let us elaborate a little bit. So अगर आपको S3T given है तो what will you do? Now you have S3T and two sets. And remember that they are two orthogonal sets. Well, sorry, they are two orthogonal directions, or you can say they are two orthogonal segments. So it's like that you are a vector S3T. Like you can take an example. Given a three-dimensional signal, phi1t and phi2t can be seen as x and y axis. Okay. So this 3D signal means that it has some x1 comma y1 comma z1 signal, or you can say vector. So let us say this is a sort of a vector. So these are two x and y axis. So you need to find out the z. Okay, that is the simple terms. You have to find it. So how do you do that? So you first project S3T along phi1t, then you project S3T along phi2t. You sum both of them. It means you will find the component in the xy plane and subtract that component from S3T. So you will get the component which is now orthogonal to both phi1t and phi2t. Okay. So how will you do that? Simply write that S3T minus the logic which we have used here, this one, that S21. So you can say this is S31 phi1t minus S32 phi2t. Now this, let us say, is G3T. Now this G3T would be orthogonal to this, the both. So G3T would be orthogonal to both phi1t and phi2t. And now you divide G3T by its norm. Okay. When you divide G3T by its norm, so you will get the third orthonormal. That is what we are doing. GIT is nothing but SIT. और अब तक जो आपने वेक्टर्स निकाल लिए, let us say 5j, that's why this I minus 1 comes. Okay. Let us say this is 4. So if you are on the fourth signal, so it is assumed that up to the third signal you have derived 3 orthonormal vectors which are represented by phi1, phi2, phi3. And Sij is nothing but the projection of this Sit onto each one. Now what do we do that is, let us say, जैसे कि अब आप देख सकते हैं कि if this is my x and this is my y and suppose this is my z, बहुत easily आप इसको समझ सकते हैं. Now suppose this is my any vector, 3-dimensional. Okay? So if at all I need to find the projection of this vector onto this plane. So this is the projection of this. Let us say this will be represented by some, you can say S. So this is its projection of S on xy plane. So how do you do that? You simply project S onto x, onto y, add both of them, and you will get this. Now you know that this vector which we have written, I think it should have a downward spelling. I don't know that. I think that doesn't matter right now. This would be orthogonal to this whole plane. So that is what we do. So we can move. So now we have to visualize this thing in n-dimensional space, and that is what we have done here. Okay. So you can say that if I represent this as equation number 2, and I represent, I think, G2T1 as equation number, you can say this is 2, and suppose I write this as 3. So equation 2 is a special case of equation 3 with I equal to 2. Okay. For I equal to 1, function GIT reduces to SNT. Okay. So if we have obtained GITs, so given the GITs, we may define the set of basis functions phi nt is equal to GIT divided by under root of 0 to t GI square dt, which I is equal to 1 to, which form an orthonormal set. Now there are two things to say, that we would have n less than equal to m. Okay. Now m is the number of signals we started with, n is the number of orthonormal signals which we would generate through this Gram-Schmidt procedure. Now this has to be there, that n will always be less than equal to n. So we will write, so when is n equal to n and when is n strictly less than. Sorry. So that's the signals. S1t, S2t, and SMT form a linearly independent. The signals form a linear independent set in which case then we have a strike through here. Okay, and second is signals S1t. So it is not functioning properly, so let me write it down in the space which is left. So signals S1t, S2t, and SMT are not linearly independent. Sorry, I have to put a page. Not linearly independent. In which case, these 2 points are very important. In which case, n is strictly less than m, and function GIT is is 0 for I strictly determined. Okay. So what do we really mean by this, whatever we are writing? So what we are saying is, कि अगर let us say if you start with 4 signals, S1T, S2T, S3T and S4T. Now if those 4 signals are linearly independent, it means one cannot be expressed as a linear combination of others, anyone. Okay, then that set is linearly independent. So if at all you start from the Gram-Schmidt procedure, you will land up with 4 orthonormal signals. Okay, आपने 4 सिग्नल से स्टार्ट किया था और आपने 4 ही सिग्नल्स का ऑर्थोनॉर्मल सेट क्रिएट किया because of this procedure. But there is a case when, let us say, one of the signals can be expressed in terms of others. It means all m signals, or the signals, the number of signals from which you start, they are not linearly independent. In that case, what will happen is that the number of signals which you will obtain through the Gram-Schmidt procedure, they will be less than the number of signals you started with. Okay, if at all you start with m equal to 4, so you might land up to with 2 or at max 3, you can say, number of orthonormal signals. So G4T would be 0. Why? Because one of the signals would be lying in the plane of other signals. जैसे कि एक simple कह सकते हैं. Now suppose you start with suppose 1, 2, 3, three-dimensional signals would call, and you start with 5, 6, 7 suppose, and you have another vector, suppose it is say 2, 3 and 0. So one lies in the xy plane only. So maybe in such case you will land up with only 2, you can say, orthonormal vectors, which would suffice for this set. Okay, but anyways you cannot exceed the number of this. It means n cannot be more than 3, because right now we are considering 3 vectors. Okay, so जिनसे आप start करेंगे उससे ज़्यादा तो नहीं हो सकता. I am not elaborating why it cannot be, because this directly follows from the linear algebra. Linear algebra से आप directly इसको link कर सकते हैं. If at all there is some issue with your understanding there, then we can definitely discuss. Okay, there is no problem in that. But for the sake of moving ahead, I have to assume that you know this. Okay. So let me write down 2 things. That there are 2 examples of this. One is the conventional Fourier series. The conventional Fourier series. Okay. What is you are doing there? You are doing the same thing. Fourier series of a periodic series. Okay. And second is, this is first, band limited signal expansion in terms of its samples taken at the Nyquist range. So in both the cases, we do this sort of a expansion, okay, in terms of orthonormal functions. जैसे कि आप Fourier series में you know that जो आप complex exponentials use करते हैं, they are all orthogonal to each other over the period, okay, of the period of the signal. Similarly, the band limited signal के केस में हम लोगों ने ये study किया था, I think in our initial lectures, that any band limited signal can be expressed in terms of a series in which the basis functions were shifted sinc functions. Okay. So that is what we have already done. It means we know. But there are 2 distinctions. Let us say if we compare what we have done with these 2 things which we have already done in maybe another courses as well as this course. Let us write down these 2 distinctions. 2 distinctions. Okay. The first is form of basis functions phi and t has not been specified. Okay, this is important. In both of these examples, this conventional Fourier series had complex exponentials and this had sinc functions. But whatever we have done above, we have not yet specified. It is quite general. It means from the set itself we can create phi 1t, phi 2t, and phi n. So they have not been specified. That is not sinusoidal functions, not as in the case of Fourier series, not sinusoidal functions as in Fourier series, or sinc functions expansion of band limited signals. Okay, so we have not specified. Secondly, there is important thing here using finite number of terms. They are using finite number of terms is not an approximation. Okay. Wherein only the first n terms are significant. Wherein only the first n terms are significant. Rather, an exact expression where n and only n terms are significant. Now, what do we mean by this? Let me just clarify. See, generally these two expansions, one is the conventional Fourier series expansion and the band limited signals expansion, they have infinite terms. Okay. So in order to make them usable, you truncate the series up to some point. Let us say capital N number of, you can say you take the complex exponentials and you create an approximation to the signal. The same happens for the band limited signals. So that is what it is said. But whatever we have done above, we get a definite number, let us say N of orthonormal functions. And in terms of those N orthonormal functions, we can write our each of the functions, each of the N functions. Okay. So what is said here is that here using finite number of terms, that is जो Gram-Schmidt ने आपको capital N number of terms दिए हैं, अगर आप उसको use करते हैं, that won't lead to some sort of an approximation, which it does in the case of these two, you can say, things we have used. One is conventional Fourier series. If you take only n terms, similarly, if you take only n terms for the band limited signals expansion, then you would get an approximation. So here using finite number of terms is not an approximation. It means you only need exactly n terms and n terms are required, wherein only the first n terms are significant, rather an exact expression where n and only n terms are significant. Okay, it means यहाँ पे आपने m signals का से जो n signals का set create किया है, उन n signals में सिर्फ और सिर्फ n ही चाहिए और उन n से आप approximation generate नहीं करेंगे, उनसे आप correctly each of the functions को generate कर पाएंगे. So this is what is the argument. Okay. So in order to complete our study, it means at this point we are done with the Gram-Schmidt procedure. We can see one example. Okay. So I am drawing the example for you that you try doing so on this set. So let us say you are given this value is 1, this is t, and this is your S1t. Okay. And then you draw this S2t, S to T. Okay. So this is like this. This is 1, this is 2. Okay. Then you have this S3T. Okay. And we have one S4T. So we want to apply the principle we have learned over this. This is S4T. This is T. This is T. So you are given. So given S1T, S2T, S3T, and S4T as above. Use GS procedure to find phi IT, where I will be 1, 2, up to whatever. Means let us check. अभी तो नहीं पता हमें कि ये इसमें 4 आएंगे कि 1, 2 या 3 आएंगे. Okay, so we have to start the procedure and see. So first of all, the task is to obtain the energy. Let us say if we start with S1T. So what is the energy in S1T? So energy in S1T. I don't know if some of you would like to try this out. So maybe I can give you 3-4 minutes in order to. So what I would say is that you just draw these. If you have a pen and paper, just draw these 4 signals and start doing this procedure. And then another 3 minutes or 4 minutes, maybe at 11:17, I would start doing it myself. Okay. So we'll talk at 11:17. In the meantime, you try doing this. Those of you who have a pen and paper, try this out. Create the whatever number at max 4 can exist of orthonormal functions. I'll start in another minute. That is, I would solve this problem so that you know that how do you apply this procedure. You can clearly see that the time of interest would be 0 to 3 because that is the maximum time any of the signal is defined for. So let us first of all find out the energy in S1T. So this would be integral 0 to 2 because it is defined from 0 to 2. It is 1 square dt which is equal to 2. Okay. So the first signal, that is phi 1t, as we already seen, it will be S1t divided by the energy of S1t, which is equal to S1t divided by, sorry, it has to be root of this root. Okay, so this is our first, you can say, signal, which is as per the procedure. Let me just go back and show it to you. The first step is S1t divided by the root of the energy. Okay, so this we have done. Now let us take S2t and try to project it on S1t. So now project S2t onto phi 1t. So for it, first you need to obtain the inner product. Okay. Obtain the inner product, which is equal to integral. Let us see the S2t and phi 1t. So phi 1t is defined from 0 to 2 and S2t is defined from 0 to 2. So both are defined from 0 to 2. So let us do 0 to 2 S2t into S1t divided by root 2 dt. So if you can see from the figures, if someone has drawn it on a sheet of paper, so this is S1t and this is your S2t. So from, you can divide the integral into two parts, that is 0 to 1 and then 1 to 2. So let us say this is 0 to 1. So 0 to 1 both take a value of 1 dt plus 1 to 2. So they take a value, one takes a value of minus 1, another takes a value of 1, so it will be minus 1 into dt and whole divided by root 2. So this will lead to 1 minus, let us say what it will lead to 1 divided by root 2. So this is 0. So if at all we know that this is C21, so if C21 is 0, it means S2t is already orthogonal to phi 1t. This we have seen as C21 is 0, we know, or we can comprehend, or we can observe, or we can say S2t is orthogonal to phi 1t. So now the purpose is to simply obtain the energy of S2t. So phi 2t can be defined as S2t divided by energy of S2. So this is what? S2t integral, let us see energy of S2t, that is 0 to 2 S2 square t dt, which is equal to S2t divided by under root of, you can write from 0 to 1 it is 1 square and from 1 to 2 it is again 1 square, it is 1. So you can 0 to 1 1 square dt plus 1 to 2 1 square dt, which equals minus 1 square. I am just writing everything clearly so that if you go back and read the notes, you know all these steps. Okay, that is under root of, so this is simply 1 plus this would be 1, 2, 2, 3, 3. Okay. Sorry, 3, 1. So this would be equal to S2t divided by. Okay. Now the third step. So let us, I think, do it stepwise. So this is the first, this is the second thing. Okay, now the third thing. Now project S3t onto phi 1t and phi 2. So first obtain C31. It is equal to integral. Let us check if we want to project S3T onto. So I am just writing the values now because I think this is quite straightforward to see. So this should be 0 to 3 S3T into phi 1T dt. But this comes out to be 0. So C31 is 0 and C32. So I am not explicitly solving it. I think this can be easily done. S3T into phi 2T dt, which is equal to minus of root 2. Okay. So once we have both the things, so now we can obtain G3T. Let me write. This implies that your G3T would be S3T, okay, minus this is 0 plus root 2 times 5. Okay, so this is your G3T. Now if you divide it by the norm, so you will get the phi 3T. So phi 3T would be G3T divided by energy of G3, which is equal to. Okay, so it has unit energy. So this is 1. So this is G3T. So this I am not calculating. This would be 1. Okay, if you calculate and check, this would come out to be 1. Okay? So phi 3T would be G3T. Now the fourth step is project S4T onto phi 1T, phi 2T, and phi 3T. Okay, so let us check what is C41. So C41 is root 2, C42 is 0, C43 is 1. So I am not writing, or let me just, I think it is fine because it should be very clear. So S4T is 0 to 3, so 0 to 3, S4T into phi 1T dt. Generally, when you define like this, you will have a division by the norm of phi 1T. Now, this norm of phi 1T or square of the norm of phi 1T, that is 1 in all the cases. So I am not writing this down. Okay, some may division hoga norm se, but I am not writing it down because it would be 1. Okay. So similarly, you can do for C42 and C43T as well. So hence, your G4T would be S4T minus root 2 phi 1T minus, because this is 0, phi 3T. Okay. Now this you find out that this is equal to 0. Okay. Now it means that it is sufficient that we have only these 3 orthonormal functions. Why? Because S43 comes out to be lying in the same plane as that created by the 3 segments. Okay. Thus, this was a good example. Okay, S4T is a linear combination. Of phi 1T and phi 3T. This is a homework. Check. Okay, and consequently, the dimensionality of the signal set is n is equal to 3. Okay, so if I now try drawing all the phi's, let me just draw it. And at that point, we can close the session for today. This is 0 and this is 2. So this would be like this. this is 1 by root 2. Okay, then phi 2t okay, and finally you have phi 3t. This is from 2 to 3. So this is so at this point I would say that we closed the discussion on Gram-Schmidt procedure. Okay. So from next class we would start with random processes. Why? Because we need to now introduce noise into the system. We need to know the structure of the noise, and with the structure of the noise, then we would come to the final part of this course, that is deriving the modulation schemes and studying their performance. Okay. So now next class on Tuesday we will start with random processes. So we are done for today. Those who need to talk to me about something, they can stay back, others can leave.